Okay, we are going to start chapter 7 today. Chapter 7 is about estimates and sample sizes. The practice problems at the end of the chapter 6 notes that I gave you, there's 6 practice problems on that last page. Those are actually your third chapter 6 assignment. And there's a drop box for it now. If you go to Show Me, Chapter 6, Assignment 3, I just pulled those problems into a separate document. So which is basically a review of everything we did in Chapter 6. The only difference in this and what you have printed out is that I've spaced it out more so that you would have more room if you're actually doing it in Show Me. So where we are now is we're going to start Chapter 7. Chapter 7 is about estimates and sample sizes. So if you've got your notes printed out, a point estimate is a single value, which is why it's a point, a single value for x, that's used to approximate or to guess the value of a population parameter. You need to remember that population parameters are mu and sigma, and there's also a population proportion that's called p. The best estimate, the most unbiased estimate for mu, the population mean, is the mean of a sample taken from that population, which is x bar. The most unbiased estimator for the population proportion, p, is a proportion from a sample taken from that population, and that's called p hat. And the most unbiased estimator for the population standard deviation, sigma, is the standard deviation s from a sample taken from that population. A confidence interval in this chapter is going to be what we call an interval estimate, and it's an interval of numbers used to estimate the true value of the population parameter, either mu, p, or sigma. We won't do any confidence interval estimates for sigma, although we will use s to estimate the value of sigma at some point. We're going to talk about something called a confidence level. Confidence level is going to be basically how sure of you on your answer. The confidence level is the probability, and we're going to use the expression 1 minus alpha, 1 because the total area under the curve is 1, and alpha is going to be the area that's on the outsides of that interval. So the confidence interval is going to be between two spaces, 2 marks on the normal curve. And some of you, I noticed, had problems finding the middle 50%, the middle 60%. Those problems are actually to lead you into how we do confidence intervals. So we'll kind of go over how to do some of those today. So the probability is 1 minus alpha, which is the area, and that will be small in the tails because alpha is going to be the probability that we don't get the answer right. It's going to be the probability that we're wrong. We want to be highly confident that we're right. And that what we're going to say is that the interval actually does contain the population parameter that we want. And when we interpret a confidence interval, the way that we're going to interpret it is that we're going to say that we are some percent, like 90% or 100%. Well, no, we'd never be 100% sure because we never have a population. 90%, 99.9% maybe. 95%, 98%. Anything above 90% would be, you know, an appropriate confidence level. And what we're going to say is that we're that percentage confident that either the mean or the proportion of the population, that the mean or proportion of the population, whichever we're looking at, is between some number and another number that's larger than that first number. We're also going to talk about something called critical values. A critical value is the number on the borderline that separates the sample statistics that are likely to occur from the ones that are not likely to occur. So what I'm going to do, before we go any further and start working examples, I'm going to try to give you a visual of what we're doing. And I'm going to do that by going and pulling a problem out of Chapter 6's notes. No, I don't want to do the assignment note. Let's see. So we'll take a quick review here of Chapter 6, and this is in your Chapter 6 notes if you've got those handy. It says that records indicate that the packages shipped by a certain trucking company have a mean weight of 510 pounds and a standard deviation of 90 pounds. And 100 packages are going to be shipped. What's the probability their mean weight will be, the problem asks us, more than 530 pounds? What's happening with that problem is we're given this information here, and asked to figure out the answer to this question. What's the probability that the mean weight is more than 530? And just to kind of give you a quick review of Chapter 6, what that means is that this is going to be a normal distribution. And that the mean of this normal distribution is going to be 510. Because the mean of the population can be assumed to be the same as the mean of all the samples of size 100. And because of these two things, we know that the standard deviation of all the samples should be equal to the value of the population standard deviation over the square root of n, which would be 90 over the square root of 100. And actually, when you do the math, that turns out to be 9. So this would be 519. This would be 528. And then the third mark up the curve would be at 537. So in this particular problem, they're asking us what's the probability that it's more than 530. And 530 would be the probability that's located in the upper part of the curve up here. okay? It would be this little area up here. And the way that we would do that problem is we would use normal CDF, and we would start at 530, and we would go to positive infinity, and the curve has a mean of 510, and a standard deviation not of 90, but 90 over the square root of 100. And we would do that on the calculator. And so the central limit theorem would tell us that the probability of a single package is not going to be the same as the probability of a mean of 100 packages. So the probability for the mean of 100 packages being more than 530 is equal to this probability statement in the calculator, and that actually then is equal to 0.0131. Which is only about 1.31%. So that's not a very high probability. Okay? Now I'm going to try to recast that problem with the same basic information into a problem like we would do in this chapter and show you how we would do it using the methods out of chapter 6. So using that same information, we know that the mean of the population is supposed to be 510. And the standard deviation should be 90. So if we took a bunch of samples of 100 each, we could use that information to find a slightly different probability question. Let's suppose that all of their trucks can carry 100 packages. But sometimes that truck has to stop at a weigh station. Now, they obviously want their truck to be able to pass through the weigh station without getting fined or being too heavy. That makes sense. They don't want to have to pay a fine. They don't want the truck to have to be slowed down. But they also want to make sure that the truck is carrying enough weight to make it efficient for where they're going to. They don't want it to contain too little weight. They want to be sure they get it packed in there evenly. So what they would like is they would like to know between what kind of average weight should they keep their truck and not have to be stopped at the weigh station or not wasting money because the truck's not loaded enough. So maybe they would like to find that interval of samples of 100 packages. Where this would cause them to lose money. Because the trucks are too heavy. But on the other end, they would also lose money because they weren't efficiently using their gasoline. So what they would like, it was 90% of the time, they would like for their truck to be loaded with packages in this interval. Okay, they want to keep their packages in that interval 90% of the time. That means, because this is 90% of the time, they're trying to keep it down to less than 5% of the time. So they want to keep that down to 5% of the time, but they also want to keep this down to 5% of the time. So in terms of what I was just telling you in this problem, this is your confidence level. And when I said something about Z alpha over 2, Z alpha over 2 is this value. In terms of Z-scores. Z alpha over 2 is going to be the part that is the boundary line that cuts off this top 5% from the rest of the curve, or cuts off this bottom 5% from the rest of the curve. And later on, we're going to see that that's also called the critical value. We're going to refer to that as the critical value. Now, we can put what we've already learned together to be able to figure this out. If I'm trying to find this critical value here, what I'm trying to find is the Z value that puts 5% to the left of that Z value in the tail. And that's an inverse norm problem. Inverse norm 0.0501. That'll tell me how many standard deviations below the mean I am. And that tells me I'm about 1.64. We'll just round that off to 1.64. Standard deviations or standard errors, which is, I'm going to calculate from this information. And this Z-score is going to be the same exact number, except it's going to be positive. And then because the standard error of the curve, the standard deviation of this curve, because of the central limit theorem, tells us that that's going to be 90 over the square root of 100, which was 9. Oh, I don't know how I put them. That's not 100, that's 510. Sorry, guys. I was thinking about that package, about 100 packages. So this, again, this is going to be 519. And this is going to be 528, and then on up here, 3 standard errors away is going to be 537. And then down here, 510 minus 9 will be 501. And 501 minus 9 will be 92. And then the last one down here is going to be 83. So when I talk about Z alpha over 2, you're basically counting how many of these little chunks that you're moving to, okay? Now, last time we also said, you know, you don't actually have to have that Z-score. You actually could just go ahead and find out what the value is, your upper and lower numbers here. So we could actually find this. Instead of using inverse norm with that, we could go inverse norm and keep that same area, but use the mean of the curve and the standard deviation of the curve, which again, that's going to be 90 over the square root of 100, which is just going to be 9. I'm going to go ahead and just write it down as 9. And that will be a weight. And it says this line is at 495.196. And then if I do the same thing with this one's going to be 1 minus 5% because the area up here is 5%, and there's 1 minus 95%, or 1 minus 90%, 1 minus 5%. I don't know where I'm getting short-circuited here. This is 5%. All of the area under the curve is 100%, so 100% minus 5% leaves us with 95% down here. So this is going to be inverse norm. And you can either put 1 minus 0.05, or you can just put the 95. And then the mean of the curve is 510. And the standard deviation is 9. And rather than having to go through the Z-score, we'll actually have the upper package limit. So what we found here is that the middle 90% of their packages weighs between 495.2 and 524.8 pounds. So they know that they're making efficient use of their trucks if all of their trucks weigh somewhere on this interval. Okay? And so they're going to try to stay between those two numbers. So we've made the conclusion in the language of Chapter 7 we're 95% sure all samples of 100 packages have a mean weight between 95.2 and 524.8 pounds. So this is a problem we worked by knowing how to do what we did in Chapter 6. But this is a lot of work. It takes a long time to do this problem by using the methods in Chapter 6. So, the point of going through today's lecture is to get you to where you don't have to do that much work. We're going to let the calculator do most of the work for us. So I'm going to skip over some of the notes. You can just mark through the parts that I've skipped over. We're going to go to the slide, the part of your notes that talks about margin of error. If you want to know how to find those two problems, this PowerPoint is posted in the Chapter 7 notes. So if you need to find those two that I skipped over, this is how you do it, and you'd do it on the calculator. You wouldn't do it by hand. So visually, this is what we're looking at. We're looking at a confidence level which is between two upper and lower, we might think of it as fences or boundaries or limits. And Z alpha over 2 is a very small area in the tails, because if we're in that area, those tail areas, that means that we have packages that aren't within what we want. So the margin of error, the symbol for it is E, and it's the maximum distance between the point estimate and the actual value of the population parameter that we're looking for. The margin of error is also sometimes called the maximum error of the estimate, but most of the time we will use the language margin of error because it's just easier. So if I move back one PowerPoint slide, on this PowerPoint slide, your margin of error is the distance from the center of the curve to the upper boundary, or from the center of the curve to the lower boundary. That's the margin of error. Visually, that's what it is. So as an example, given that we know the margin of error, E, is 0.15, and that some value we're going to call P hat, that's a population proportion. Population proportion is 0.524, and somehow that one has escaped me. Ah, here we go. We're going to find the confidence interval. So here's that problem. This is what that means. It means you have a normal curve. The population parameters are normally distributed around, this means this is a sample mean. So we're going to use it as the center of our curve because it's the best guess we have for P. So that comes from a sample. Your margin of error is this distance right here. That's what's called the margin of error. And we know the amount of E is 0.15. Okay? So what this is saying basically is, in order to figure out what this value is, what we need to do is we need to take the center, 0.524, and add to it 0.15. And that's going to give us 0.674. And then in order to get this number, we're going to take our 5.24, or a 0.524, and subtract from it the 0.15 because we're going below it, so we're going to subtract. And that comes out to be, I think, 49. Now, I'm going to do the calculator. .374. Okay? So that's what that actually means. That's a picture of what they asked us. And then if we had to word the conclusion, then our conclusion would be we are some percentage, we don't know what the percentage is, certain that the population proportion and the symbol for that is just a P, is between 0.374 and 0.674. So that's kind of how it all fits together. Does anybody need to ask a question? We are going to be able to figure out what the percent is. I want you to get a pretty solid understanding of exactly what we're doing, though, trying to link it with Chapter 6. Okay. We're going to do a couple of these just to make sure you know where we're going with this, because I really want you to understand what margin of error is. Makes it easier to understand the whole chapter if you understand that. It says, given that we have a sample mean, that's 43 minutes, and a margin of error of 6 minutes, find the confidence level interval for the population mean. Now again, we don't know the percentage yet. We don't have that because they've already done that work for us. They're just giving us this information. So in order to make sense of the problem, we know that the sample mean is our best guess for what the population mean is. That's what we're trying to find. But the best guess we have for it is X bar, and that's 43 minutes. So we'll go ahead and use it as if it really were the population mean. And then it says the margin of error of our guess is we might be wrong by 6 minutes either way. So there's your margin of error on either side of the mean. So the confidence interval means I need to know the value of this number and of this number. This number would be 43 minus 6. And 43 minus 6 is 37. And this number would be 43 plus 6. So that would be 49. So then if we had that percentage that they had used to come up with that margin of error, then we could say we are some percent sure that the mean time for whatever it is they're measuring is between 37 and 49 minutes. So we did one with a mean, one with a proportion. And here's another one with a mean, and this one's a little bit different, but I want you to keep getting the concept of what that margin of error is telling you. It says this is the limits, this is the interval. They want us to go back and find the sample mean and to find the margin of error. Now remember what we're doing here basically is we're going backwards. So we would like to know this, and we'd also like to know this. And what we do know is that the value of E is going to be the same on both sides, but we need to know what that middle is. So this lower number is 25.14. And this upper number is 31.66. Where do we find the mean? That's right. You're finding the midpoint of the confidence interval. You add those two endpoints together and divide by 2. So X bar, you add 31.66 to 25.14. And get 56.80. And we divide 56.80 by 2, what do you get? Mm-hmm. And it's 28.4 between 25 and 31. Mm-hmm. So if we know that this is 28.4, then how do we figure out what this is? Just, yeah, subtract this number from this one. I know you're here.
Okay, thank you.
All right. So it's 3.26. And if there's any doubt that this is 3.26, you can prove it to yourself a couple other ways. You could take 31.66 and subtract 28.4 from it. And you would get 3.26. The other thing that you could do, and I'm giving you 3 different ways, so you pick one of these that you're going to do all the time. This is E and this is E. E plus E is 2 E's. Okay? That whole thing is 2E wide. And 31.66 minus 25.14. Excuse me?
Is that supposed to be addition or subtraction on the right side?
No, it's going to be subtraction because I'm finding out how far is it from here to here. So I'm going to take the high number and subtract the low number. Okay? And if I do that, I get 6.52. So if I divide both sides by 2 using some of your rusty algebra skills, I get 3.26, which is what I'm supposed to get. So the margin of error is the distance from the middle down to the lower value. It's also the distance from the higher value down to the middle. Or it's the distance from the low to the high, and since that's 2 margins of error, find the difference between those 2 numbers and then cut that in half. You'll get the same thing every different way you do it. So this is the formula for margin of error. And it consists of 2 pieces. You don't need to worry about memorizing it. You're not going to be using it except when I tell you to use it, which won't be very often. So margin of error consists of 2 pieces. The first of the 2 pieces comes from the sample. It's the standard deviation of the sample means, which is called the standard error. And the other part is how many standard errors. That's your z-score. So you take your margin of error and x bar, the sample mean, which is our guess for the middle, minus the margin of error gives us the lower limit, and x bar plus the margin of error gives us the upper limit, and then we'll, based on whatever that z is, we'll know the percentage from that and be able to say that we're pretty sure that that level of confidence sure that the mean is on the interval that we wind up with. Okay? So now we're going to do some examples. Simple random sample of birth weights in the United States has a mean of 3,433 grams. Standard deviation of all the birth weights is, that's the population standard deviation, is 495 grams. We're going to use a sample size of 75. And we're going to construct what's called a 95% confidence interval estimate of the mean birth weight in the United States. So here's how we do that. We go through the problem and we pick out what we know. This is a sample mean. Oh, sorry. Thank you. Get the calculator out of the way. So this is a sample mean. X bar is 3433. But for some reason, even though we don't have the population mean, we know it's standard deviation. So that sigma is equal to 495. And our sample size is 75. And this was your clue that this was the population standard deviation, because it says all. And we want to make a 95% confidence interval estimate. Now we know the central limit theorem applies to this. The reason we know that is because regardless of whether birth weights are normally distributed or not, our sample is more than 30. So it tells us that we can work the problem because we know that. So So we take the information we have and we make the assumption that these means are normally distributed because they should be with a sample that big. And our best guess for the value of mu which is the mean of the sample means and the mean of the population. Our best guess for that value is going to be the sample mean that we've got, because it's the only evidence we have. So we put 34, 33 in the middle. Then the other thing that we know is that since this is sample size, random sample, we're talking about sample means, we need sigma x bar. And we have sigma, and we have a sample size. So we use that to estimate the sample standard deviation, or the standard deviation of all the samples. So that's going to be 495 over the square root of 75. Now I'm going to go ahead and calculate that out, but I'm not going to use it. I want you to have an idea of how much that is. So our standard deviation is about 57.2. Our 95% confidence interval is going to be the part in the middle. And that means that the alpha over 2 value is going to be 1 minus 0.95 divided by 2. And since 1 minus 0.95 is 0.05 divided by 2, this is 0.025. And that same 0.025 is on this end. So in order to calculate the margin of error, this is the only time I'm going to make you do this, is with this first example. To calculate the margin of error, you remember that your formula for margin of error is Z alpha over 2 times your standard error. And Z alpha over 2 is the Z score here and here. This one is negative, this one is positive. Those Z scores are the Z score that cuts off 0.025 in the tables. And we can find that using the calculator. and we get negative 1.959, so we'll call that negative 1.96, which means this one then would be positive 1.96. And remember, that's the z values. That's not the actual value of the weights. That's just how many standard deviations you are away. So we're going to replace, in this formula for E we have here, we're going to replace z alpha over 2 with 1.96. And that's going to be times this 495 over the square root of 75. And since I've got that on my calculator already, I have my value of z up there already. I can just multiply times, in parentheses, 495 divided by the square root of 75, and there won't be any round off error. So my margin of error on this side, I'm going to subtract 112.02. And on this side, I'm going to add 112.02 because this one is the mean plus that much. This one is the mean minus that much. So there's your error. The amount of your error is about 112.02. And if I take the mean, I get 320.97. I'm sorry, 3320.97. And then if I do the same thing, I get 345.45 or 3545.03. And those are the numbers that answer my question.
So on a test, do we need to do all of that?
No, but I want to make sure you understand the process that we're doing. Okay? Mostly because when you're trying to get the definitions, if you can't understand where everything went, it's hard to remember what that word meant. Okay? So there's our confidence interval. And then in order to answer the question, now here's the thing that if we're going to do any rounding, this is an important idea. This means if that birth weight is 3320, it's in the alpha over 2 part. So we need to round it up to a whole birth weight if we're going to round. So we're going to round this up and say that's 3321. And the same thing here. 3545 is actually within this part, so on this end we're going to kind of round down. So that's your conclusion. We're 95% certain that the mean birth weight for all births is between 3,321 grams and 3,545 grams. So that's the last part of the statement. Now I'll show you how the calculator will give you the same information. So what we're going to do is we're not going to go to the bars key. We're going to the stat button. Okay? Go to the stat button. I'll pull this down kind of in the middle so you can see it better. And I want you to go over to the menu that says tests. Now what we're doing is not a test, but it happens to be on the test menu. Press your stat button and then right arrow over to where it says test at the top. Okay? What we want is an interval. So go down to number 7, which says Z-interval. You know what a Z-score is. This is based on using standard normal tables. So we want a Z-interval. And it asks us a series of questions. The first question it asks us is, do you have data or do you have statistics? If I had data, it would have to be in a list. So if I were going to select data, my screen doesn't look the same. It asks different questions. But I don't have the data. I don't have those 75 birth weights that they use to get that sample mean. I have the statistic. So
if they did give us one, we'd go in and put it in and then
choose data and tell it where the data is. Okay? And the first question it asks us after we've chosen data, it says, okay, what is your population standard deviation? Okay, our population standard deviation, and it didn't ask us the standard error, it said, what is your population standard deviation? That's all it asked us for. It's going to do the arithmetic. So our population standard deviation is 495. And then it says, okay, what is your sample mean? 3433. And then it says, okay, what is your sample size?
Wouldn't you do the standard deviation, wouldn't you do the 495 divided by?
No. No, because it didn't ask us for sigma explosion. Remember, it asked us for sigma. And we're giving it in, so it knows how to calculate that. It has that built into it. It knows the formula. So all we have to do is let it do all the arithmetic for us, which is great. And the last question it asks us is, well, okay, what's your confidence level? And we're going to enter it as a decimal. And you only have one choice after that. You let it calculate. And there's your answer. Okay? So all that time we spent doing all of this, it takes just long enough to punch the numbers in the calculator. Okay? And we can go straight to the conclusion. So with that said, we're going to go to the next example, but we're going to come back to this one, so keep that one handy. We're going to go to part B. The first thing that we need to do in Part B is look and see what all of our information is. Still have a sample that has a mean of 3433. We know that the standard deviation is 495. But then the last thing that it tells us is our sample size in Part B has changed. And we have a sample of 75,000. And we're again going to construct a 95% confidence interval. So we have everything we need. We'll get the calculator. We go back to Stat, over to Tests, and down to Z interval. And the only thing that's changed is the sample size. Okay? The sample size is now 75,000. And here's your new confidence interval. And that's the way to write it as a probability statement. Did I put, should be 3, 4, thank you. So that should be, well, let me just scratch out the whole thing. Okay? Now I'm going to go back and pull the numbers from the other one. Which interval is wider? The Part A answer, right? Because 34 is above 33. And 35 is higher than 34, 36. Okay? No, it doesn't make any sense. I'm looking at what did we do? Did I transpose a number when I wrote it down? Let's go back and double check the numbers. 35, 45, and 33, 21.
That's right. It's double right there.
Okay. So let's put things where they go. This one, here's 3321. Here's 3545.
Calculator.
So 3429 is more than this, right? 3400 is more than 3300. And 3436 is less than 3545.
And then 36.
So that's the sample size of 75,000. This is with a sample of 75. The sample of 75 has a wider interval estimate. The reason it's a wider interval estimate is because the margin of error is bigger. Okay? Remember, both of these are centered over X bar, which is 3433. That's centered over 95% in both cases. 95% has the same z-score regardless of what you put it on. It's still going to have the same number of standard deviations. So what changed was this. I want you to remember, for a sample of 75, sigma x bar was 495 over the square root of 75. And that was equal to about 57.2. Okay? But when we change that sample size to 7,500, your margin of error went down to, oh, yeah, I left out a zero. Zeros make a big difference when you don't put them in the right place. .807, which we call about 1.8. So when you compare those two numbers, sample size has a lot to do with it. .8 is a whole lot smaller than 57.2. Okay? That's what made the difference in the intervals, was your sample size. It made made a big difference in the amount of your margin of error, which went from this to that. Okay? Remember where your margin of error is. This is the margin of error for that one, but this is the margin of error for the pink one. Look at the difference in the size of the margin of error.
So the answer would be
Yes. Yes, the answer to our question here is that, since it said which one is wider, and that's because the margin of error is influenced by sigma over the square root of n. Okay? Z alpha over 2 was the same in both of them, because it's based on the 95%, nothing else. This is the only thing that changed. And it made the interval wider for the first one because the sample was small. Interval from n equals 75 is wider because the margin of error is influenced by sigma over the square root of n. Larger samples will give smaller margins of error. Smaller margins of error are smaller values of E. Now there's one other thing that we need to learn how to do for this process. And this one you can't use your calculator except to do arithmetic because it isn't dependent upon a formula. So one of the things that we're going to have to do is to be able to find a sample size that we need that's required to estimate a population mean. How big a sample do we need? The way that that formula was arrived at, just so that you understand, is they took this formula right here, they took that formula and solved it for n. Now I'm not going to show you the algebra that's necessary to do that because it's kind of a pain. But they took that formula for error because the sample size influences the error and everything else. They took that formula for the error and they solved it for n, the sample size. And when they did that, they came up with this. You will be given the formula on the test. You don't need to memorize it. But there is no calculator routine that does it for you. So here's an example of how that formula works. It says, what size sample do you need to estimate the mean white cell blood count in cells per microliter for the population of adults in the United States, and assume you want to be 99% confident that the sample mean is within 0.2 of the actual population mean, and assume that the population standard deviation is 2.5. Here's that problem. Now I'm going to write down the sample size formula and then we're going to look and see what we have. So there's our formula. Assume you want 99% confidence. That's going to give us Z alpha over 2. Just to remind you of how this works, you don't have to necessarily draw all this out, but I'm trying to get you to remember what everything is. 99% confidence means there's 0.99 between those two values. This is the lower Z value, this is the upper Z value, and the only difference between them is that one's positive and one's negative. Okay? If there's 99% here, 1 minus 0.99 is 0.01. So this is the z-scores for 0.01 over 2, or 0.005. That means there's 0.005 right there. Okay? That's the area to the left. That means in order to find that z-score, we're going to use inverse norm, area to the left, mean of 0, standard deviation of 1, because it's z. And that's negative 2.5758, which we can round that off to negative 2.58. That means the positive one is positive 2.58. So what that means is, in place of z, alpha over 2, we're going to put 2.58. Now, if you're wondering why I use the positive one, it doesn't matter. You can use the negative one if you want to. The only thing that's different is that when you get done, you get a negative number, and at the end, when you square it, you're still going to get the same answer. Because when you square positives and negatives, the answer comes out to be positive. So I'm going to leave that right there where it is and talk about how we get the rest of it. When it says that you want to assume that your sample mean is within 0.2, that's your margin of error. The word within tells you that you're looking at your margin of error right there. I'm sorry, and I marked the wrong thing. So that tells you your margin of error is 0.2. And then the last thing that it told us at the very end says your population standard deviation, that's sigma, is 2.5. So we're going to do that arithmetic, and then we're going to square the answer. So since I've already got that number in there with no round off, I'm gonna take that negative 2.57 whatever, I'm gonna use the negative one because as I said, the answer's gonna come out to be negative until the end when you square it, and then it's gonna be positive, so it doesn't matter. So I'm gonna take that z value times the standard deviation, hit enter, divide what's left by the 0.2, hit enter, and then I'm gonna square that. And that tells me that my sample size in reality has to be 1,037, because you can't take 0.70 of a sample, of a sampling unit. You have to take the whole thing. So when,
both times I got 1,040.
did you use 2.58 instead of the whole number?
Yeah.
Okay, and it does make a little bit of difference. So here's the thing, if you're gonna do it that way, because I was just using the exact z value, be sure and show me how you did it. So you would get 1,040, okay? And if I did a multiple choice question like that, I wouldn't give you two that were that close to make you pick from. I would make sure that there would be a lot of difference between the answers, okay? And actually, that 1,040, I just looked at the end of that number, that 1,040 would actually have to be 1,041, because you can't take 0.0625 of the sample either. You still have to take the whole next one. So when you do sample size is the same thing as class width. You always round up. Regardless of what the decimal is, you have to round up. It isn't logical to do it otherwise. Now, my math lab may tell you to round differently. You do what it tells you to. But realistically, you have to round up. So those examples really pretty much cover everything that's in the first part of Chapter 7. Okay? We will start next time and finish the second part of Chapter 7. And then our exam will be next week. Okay?
So do we have enough to do any of the homework?
Let me look at the homework, because I think you might have enough to do some of it. And if you do attempt it, you're probably going to see enough to make you question, you know, what do I do now at some point. So let me get to Chapter 7's homework and look at it for you. You can do problem 1 and 2 but you can't do 3. You could do 4. You can do 5. But you can't do 6. You can do 7. And you can do 8. So there's only a couple you can't do. That way you can get started.